So I basically meant to make the title a little bit not provocative, but tongue in cheek, I guess. Fluids and solids. How come there's hydrodynamics and things like that? Okay. So judging by the list of people present right now, the contents of the first few slides will be very much known to them. But nevertheless, I would like to go through this, band theory 101 crash course, just to basically set the stage and set the language for what will follow up. So bear with me, and I hope that people in general like hearing what they already know. So I'm going to be talking about quantum mechanics of electronic fluid in a solid. So I would like to essentially define what I'm talking about, and to this end, let me remind you briefly that I am talking about electrons on a lattice. Okay, so lattice is schematically represented here on the right. It's just a set of sites that coincide with themselves upon translation. So as we all very well know, in this case, the Hamiltonian of the system commutes with the translation operator. That means that they can be diagonalized simultaneously, and the form of the wave functions of electrons in such a system has this block type. Okay, so there's a plane wave, and then there is a modulation function that is periodic in the unit cell. Okay, and basically this periodic function of the Bloch wave function, periodic part of the Bloch wave function, contains all the information about the crystal, right? So since the plane wave is completely generic, it's there for any crystal, all the information is hidden here in U. Okay, so this information, this encodes quantum mechanical information about electrons. So of course, when we solve the Schrödinger equation on a lattice, we either do it with the full Hamiltonian or with the so-called Bloch Hamiltonian, this kind of gauged out Hamiltonian for only the periodic part of the wave function. We get the information about the spectrum, we get the band structure, and we get the information about, as I said, wave function is used, right? And that in principle, all the information we can extract at the single particle level. Okay, so this knowledge of the band structure in principle leads to two types of geometry in metals in particular. So one type of geometry, which I call Lifshitz, Asbel, Kaganov type geometry, is the geometry of isoenergetic surfaces. Okay, so if I forget about the wave functions, I only take the spectrum, the band energies in a crystal, and I draw isoenergetic surfaces. They are in principle quite complicated entities. Here you see the Fermi surface of lead. Okay, so it's a very simple elemental material, yet the Fermi surface is pretty messed up. And one can basically study the geometry of this surface by means of some magneto oscillation phenomena or something like that. And basically, this is the basis of fermiology. Okay, so this is what's been happening, since mid 20th century in solid state physics. Okay, so there is another type of geometry which I will call Pancharatnam geometry. It's a geometry of wave functions. Basically, it measures or it studies or measures how wave functions are stitched together in the brilliant zone of a crystal. Okay, and importantly, this geometry, these geometric properties induce a certain corrections to observable properties of the crystal. So it's not just cute math to study. It's actually something that manifests itself in reality, in measurable properties of crystals. Okay, so the title of the talk has quantum mechanics in it. So what do I mean by quantum mechanics and classical mechanics in this case? Of course, the solution of the problem that I described, solution of the obtaining the band structure of the crystal, is very much quantum mechanical. The lattice potential varies very strongly on a very short space scale. So the solution of Schrödinger equations is quantum mechanical. However, Once the spectrum has been obtained, one can build a completely classical description of electrons responding to external smooth and weak and slow fields. Okay, and this is done by essentially taking the energy of the electron and promoting it to the status of classical Hamiltonian. Then, in the presence of electromagnetic field, we just used chiral substitution in the energy of the electron. We add scalar potential, and we can essentially write down the equations of motion for such an electron, right? So obviously, r dot is just the band velocity, and k dot, the force, contains two types of forces. One is the spatial derivative of the energy. That's like, electric part of the Lorentz force, and then there is a magnetic part of the Lorentz force associated with the presence of magnetic field. Okay, so once this is done, perhaps we take this, we substitute it into the classical Boltzmann equation. Of course, collision integral is a quantum mechanical object, but basically this is what I call a classical description of electrons on lattice. Okay, and I will not go through that, but it is very well known that one can derive Navier-Stokes equation from this Boltzmann equation and build the hydrodynamics description of electronic fluid if needed, essentially classical level. Okay, so what I would like to talk about is whether there is something else, something that knows about the wave functions of the electrons and lattice, and how this something else basically manifests itself in hydrodynamics in particular. Okay, so maybe this is really not needed, but I will switch now to semi-classical dynamics of band electrons. So this is the first correction to classical dynamics, and the best way to introduce it, and the easiest way to introduce it, and then we will need this information later on, is to consider what happens to the position operator for an electron on a lattice. Okay, so the wave function in band representation and block representation is this superposition, okay, with some coefficients c and k, and these coefficients are essentially the wave functions in band representation. So we need to know how the coordinate operator acts on these wave functions, and I put here the minimal derivation of this this formula below here. But if you have never seen this, this is very simple, right? So you essentially that on the full wave function, without representation being specified, this derivative acts as essentially d by dk, okay, d by d, right, the full momentum. And then by partial integration essentially a few times, we basically get that in the block representation, the operator of coordinate contains two pieces. It contains the expected part, which is the derivative with respect to quasi-momentum. Okay, this is the analog of the coordinate operator in free space. But there is a correction, momentum-dependent correction, which basically is given here. So this momentum-dependent correction is nothing but the Berry connection for the electron on the lattice. So the important conclusion that I would like to draw from this expression is that the coordinate of the electron and lattice depends on the quasi-momentum of this electron. Okay, so the interpretation of this formula is as follows: that basically this derivative with respect to quasi-momentum belongs to the Brillouin zone, so it belongs to the compact manifold. Basically, is conjugate to a discrete coordinate. Okay, it's conjugate to the lattice coordinate, and this correction, the Berry connection part, is more or less the position of the electron within the unit cell. Okay, so this two pieces then allow you to nail down the electron in the lattice. Okay, so what is then this semi-classical description I'm talking about? Basically, you proceed by comparison at this point. You know that the canonical momentum the kinematic momentum is this difference between the canonical momentum and the electromagnetic potential. And then you see that for the coordinate, for the physical coordinate, we obtain more or less the same structure, where this can be interpreted as the canonical coordinate, and this is the barrier connection. Okay, and writing down equation of motion is just can be done by analogy. So for the force acting on the particle, we get the usual del of the electric potential and the Lorentz force R dot cross B, where B is the curl of the actual electromagnetic connection. And the velocity basically gets modified in the following way. So there is usual band velocity here, and then there is this correction due to the barrier curvature, and that is really the quantum mechanical correction, H bar correction to the velocity. And as you know, it leads to all kinds of important effects in transport in crystals. Okay, so this barrier curvature, capital omega, is the curl of barrier connection. It basically plays the role of magnetic field in momentum space. Okay, obviously this is all very well known. So just the last introductory slide before we move on to stuff that is more related to the subject of this talk. You see that these equations for P dot and R dot involve R dot and P dot in their right-hand sides. So if we solve for R dot and P dot, we get the following two expressions for the effective force that acts on the electron and its effective velocity. And see that force basically contains the usual Lorentz force and this weird part, E dot B part, that essentially represents the chiral anomaly. That is the semi-classical manifestation of the chiral anomaly in crystals. Okay, and the expression for the velocity for R dot contains the usual band velocity and also two more pieces. One of which is obviously the usual anomalous velocity that leads to anomalous Hall effect, the intrinsic part of the anomalous Hall effect in crystals. The other part of the velocity that points along the magnetic field is what gives rise to the so-called chiral magnetic effect, to the current flowing along the magnetic field when there are barrier monopoles in the band structure of the material. Okay, so in particular, this will give rise to chiral magnetic effect in wire-cell metals if their values are basically out of equilibrium with each other. Okay, so this factor dB I included for completeness, but basically disregarded. It's a so-called density of states factor, which is here because P dot and R dot are not really a canonical pair. That's why you kind of need to renormalize the phase space volume with this D factor, but it's not important for us at the moment. Okay, so basically this is a short description of what happened in this field of semi-classical corrections to transport over the past 70 years. Okay, and what I would like to ask in this talk is whether there is something interesting that has the same flavor in the hydrodynamics of electronic fluid in a crystal. Okay, so in particular, here you see that I talked about responses to electromagnetic fields, okay, E and B. So when we talk about hydrodynamics, we essentially often talk about response to statistical forces, not actual forces, but statistical forces like gradient of electrochemical potential, right? So gradient of electrochemical potential can drive whole currents. I will talk about a chiral vortical effect in a second, but in principle, in a chiral crystal, there is current that flows along the rotation direction of the crystal or of the fluid. Okay, and this is the statistical force. It symmetry-wise is exactly the same as a magnetic field, right? It's a time reversal odd pseudo vector. But a magnetic field basically creates Lorentz force, rotation of the fluid that does not represent any real force. It's a statistical force. Okay, just like gradient of of chemical potential. Okay, so when we talk about viscosity, we talk about response to variation of velocity in real space. So it's another example of statistical force, and we know that basically there are forces associated with these velocity gradients. So the question is how to get these phenomena, and they basically, you'll see, they kind of are quantum mechanical. So the question is how to get them from the kinetic scheme based on a Boltzmann equation. So to summarize the discussion, the Boltzmann equation obviously has two parts: the left-hand side part and the right-hand side part. So this H bar corrections to the left-hand side more or less are responsible for all these electromagnetic effects associated with semi-classical corrections, H bar corrections to electronic dynamics. And what I would like to talk about is this H bar corrections to the collision integral, to see whether these geometric effects manifest themselves in collisions. So there's a disclaimer in order here that obviously collisions between electrons depend on their wave functions, because matrix elements for transitions depend on the wave function. So I am not talking about such effects. They are sort of trivially quantum mechanical from my point of view. So this is beside the point here. Excuse me. So what am I actually talking about? Let's talk about the band geometry effects and collisions. And by this, I mean that how the wave functions of electrons in a material actually affect the way the collisions look in this particular material. So to introduce the subject, to show you that something is going on, I would like to use a specific example of wild fermions. Okay, just a single species of wild fermions. You know that it's impossible to have a single species of wild fermions in a crystal, but if intervalley scattering is not too strong, perhaps this is a good starting point. Okay, or maybe I am thinking about massless neutrinos in high energy theory or something like that. Okay, but I will talk about single species of wild fermions here. So the Hamiltonian of this very simple system is very well known by now. It's sigma.p Hamiltonian, very, very simple. The energies are plus minus v times p. Okay, so v basically plays the role of the speed of light in this problem. And the two pieces of information that I will need about these fermions, and I will use it momentarily, is that these fermions, they have sort of intrinsic rotation associated with them. Okay, so they have intrinsic magnetic moments. I will talk about this a little bit later. I will use it a little bit later, but this is a quantity that is related again to the Bloch wave functions and their derivatives. So they basically, it's related to, again, how they're stitched up in the Brillouin zone. And the expression for this magnetic moment, orbital magnetic moment, is very similar to the expression for the Bayer curvature, except that it has this H minus epsilon, the Bloch Hamiltonian minus energy of the band of interest entering it. Okay, so basically for such a fermion, this orbital magnetic moment points along the propagation direction. Right, and then they have this intrinsic angular momentum that basically is helicity that is known from high energy course. Okay, so the projection of spin on the direction of motion is plus minus one, depending on whether you talk about conduction band, so to speak, or valence band for this Hamiltonian. Okay, so you can see that this factor here basically plays the role of the gyromagnetic ratio for these particles, and because they're massless, the mass in the Bohr magneton is substituted with p momentum divided by the speed of light, so to speak. Okay, so this is obviously a rotationally invariant Hamiltonian. So we know that the orbital and spin, sum of the orbital and spin angular momentum must be conserved in collisions. Okay, so we should conserve the total angular momentum. So armed with this knowledge, let's consider a typical collision, head-on collision of two such fermions. Okay, so basically I take two fermions with momenta P1 and P2, which are, head to head. Okay, and I scatter them, basically trying to approximately preserve energy and momentum conservation, approximately in the sense of drawing. Of course, energy and momentum are conserved. It's just I am trying to draw this in a semi-realistic way. So let's look at basically these two fermions interacting with a point-like interaction. So they come to a point, they collide, and they go out in certain directions. So the angular momentum before the collision here, and I'm talking about wave packets colliding. So that's the picture, essentially, the classical picture of the collision. The angular momentum before the collision is 0. So they head to head and come to a collision point. So it's the orbital part is 0, and the spin part depends only on the direction of motion, which are opposite for these two fermions. So the initial angular momentum basically is equal to 0. The final angular momentum, however, is not equal to 0 at all, apparently, from this diagram, because the final propagation direction is really not, butt to butt, for the lack of a better, tail to tail. Okay, so they're not propagating away from each other. There is certain angle different from pi. So the s, the spin angular momentum, doesn't add to 0. Okay. So there is a problem, apparent problem, with angular momentum conservation in this collision. So what happens in reality is that these two particles basically shift during the collision. They shift, and we will see that this is related to their wave functions, such that if I look at this collision, so now I look basically from z direction. Now let me look along y direction, such that the slide plane is the xz plane. Okay, so you see that the particle number 1, p1 prime, is flying away from me now, and the particle number 2 is flying toward me and has a component of momentum to the right. Okay, so basically the resolution of this is that they get shifted after the collision, and you see that this angular momentum non-conservation because of spin, this shift is such that there is a change in the orbital angular momentum that compensates exactly the non-conservation of spin angular momentum. Okay, so for these chiral particles, essentially, or helical rather particles, essentially angular momentum conservation immediately tells you that there must be something going on in the collision that is not captured by this naive classical diagram. Okay. So this is supposed to convince you that, as they say, shift happens. And these shifts in collisions are actually very well known in the context of electron impurity scattering. Okay, so they go back to 70s as one of the possible mechanisms for anomalous Hall effect. And the idea behind these shifts is very simple. So we have just discussed that the position of the electron in a lattice, on the lattice, depends on its quasi-momentum. So when you scatter electron of an impurity, you have a sudden change in the quasi-momentum. So there is a sudden change in the position of the electron within the lattice cell. And basically that's the shift we're talking about. So to get basically some intuitive feeling for this, we can assume that the potential of the impurity is actually very smooth. So we do not put it into the collision integral. We really treat it as an external potential on the left-hand side of the Boltzmann equation, for example. So such a smooth potential, the electric field of such a smooth potential will lead to force acting on the particle. So there will be anomalous velocity associated with that force, right? So if we take the anomalous velocity, Berry curvature cross P dot, and integrate it over the duration of the collision, and we assume that momentum doesn't change much because the potential is very smooth. So we basically get this result of omega crossed with difference in initial and final momenta for the shift of the electron. So this result only works for these very, very smooth impurities. For any impurities but weak impurity, which can be treated in let me just leave it at that. For weak impurities, the expression for the shift is very well known. The expression for the shift contains the difference in the barrier connections, okay, which you would naively expect to be there. But this expression is not gauge invariant. If you change the phase of the wave function, block wave function, arbitrarily, this difference in barrier connections will change. Okay, so there is this additional piece, okay, which essentially imposes gauge invariance for this quantity. So this becomes an observable quantity that does not depend on arbitrary phase choices made for the block functions. And these shifts were discussed in various contexts. They were first, I think, introduced by these Soviet guys in the context of studying the photogalvanic effects in crystals, essentially. So they were really thinking about vertical transition, optical transitions in the band structures. So the shifts for impurity collisions, this horizontal in energy shifts were discussed, I guess, in this paper in most comprehensive way, and then subsequent ones. But Kolya Sinitsyn sort of did a lot of stuff on this theory. Okay, but what I would like to talk about today is not this single particle shift, but it's a two-particle generalization. So the question I would like to ask is whether there is this shift in collisions of two electrons. There are no impurities now. There are only collisions of two electrons, which of course conserve energy and momentum. But are there shifts associated with these changes of quasi-momentum? So let's talk about this. So we need to compare the single particle collision with impurity and two particle collisions of two electrons. So the fact that the electrons are indistinguishable, they're identical particles, immediately tells us that the two particle coordinate shifts, I will try to convince you that they're not, they're there, basically are not reducible to the single particle shifts. Okay, so the argument is very simple. This single particle shift depends on the momenta of final and initial electrons and their wave functions. But for two particle collisions, say I take this electron, I cannot tell whether it came from this electron or this electron. They're indistinguishable. That means that I cannot possibly use the expressions for the single particle shifts to calculate these, two particle shifts. Okay, so basically there are two things that come from this argument. Is that individual shifts of each electron are not defined. Okay, you don't know what electron did before the collision. This particular blue electron did before the collision. However, we can define the symmetric combination of these shifts, the center of mass shift, and this becomes a very well-defined quantity. And this is the quantity I'm going to be talking about in what follows. So just to give you a glimpse of how to calculate it, basically you calculate the expression for the center of mass, essentially, of two colliding electrons. Okay, and you evaluate it before and after the collision. Okay, and then you subtract the two quantities. Of course, this center of mass will have the trivial part that advances with time with this average velocity. Okay, but this is not the part that we're interested in, right? So this is trivial, just ballistic flying. We subtract, we throw that away, and we essentially subtract these constant pieces that are here in the expression for the center of mass position at plus infinity, minus infinity, and this difference in these constant pieces is what I call the shift. Okay, so this delta R, which depends on initial momenta and final momenta of electrons, or is just the difference between these delta R's. Okay, so I will not go into derivation any deeper than that. Okay, so the expression for this shift ends up being something that is very much expected. You just take the barrier connections for the final states of the electrons, you subtract the sum of the barrier connection for the initial ones. Okay, and basically, again, this is not gauge invariant, so the gauge invariance imposed using this additional piece, just like in single particle case, where you use the argument of the matrix elements of the interaction between the initial and final states. Okay, so this expression basically generalizes the single particle shift. Okay, so it's sort of smart enough to distinguish between the cases of indistinguishable and distinguishable particles. These two cases are encoded in this matrix element, essentially, whether there is an exchange part or not. Okay, and it can be shown that if you have a red electron and green electron colliding, then this total two particle shift gets reduced to a sum of the individual shifts for red electrons and green electrons. Okay, and just for a reference, if you have seen these things, I'd like to mention that I can reproduce. Right, so these shifts were actually discussed in high energy contexts by Damson and Misha Stefanov and collaborators. But in that case, basically they always rely on Lorentz invariance, and they always consider point-like interaction to derive them. So essentially, what I did in this paper was to generalize these shifts to arbitrary system, to crystal, which is of course not Lorentz invariant, and arbitrary interaction. So long range, short range doesn't matter. Okay, so basically, for high energy guys, the application of Lorentz invariance in those works is absolutely masterful, but it absolutely is useless for crystals. Okay, but in crystals, you really need to use the solve quantum mechanical problem to derive this shift. But the results do coincide where they need to coincide. If I consider just neutrinos, massless neutrinos, I get the results that they get from Lorentz invariant theory. Okay, so this is all nice and cute, but what are they good for, these shifts? So we basically get to manifestation of these band geometry effects essentially in physical quantities, and the simplest effect to consider is to see whether they contribute to anomalous Hall effect, just like single particle quantities did. And indeed, the answer is yes. So I will not take you through the derivations, but I will just outline physical considerations that lead to these corrections to the anomalous Hall effect in the hydrodynamic regime. Okay. So I specifically did not really pause to discuss the hydrodynamic regime because definitely people who signed up for this seminar understand what happens to electronic fluid in a nanostructure if you treat it like water and you apply Navier-Stokes equations and in what regimes it's true and so on and so forth. Okay, so I wanted to concentrate on this crystal part, quantum mechanical part more. But basically, these shifts produce two corrections to kinetics. The first one is there is a change in the expression for the currents carried by the electronic fluid. So if you think about it, right? So these electrons, they keep colliding. Okay, they keep shifting. So if these shifts accumulate, if they shift in kind of the same direction, there is a sort of a effective velocity associated with that, right? If you take the change in coordinate and multiply it by the collision frequency, by the rate of collisions, it's sort of a velocity. Okay, so delta R by delta T is velocity. So there is a current associated with these shifts. Okay, and to obtain it is very simple. You take the shift, the shift, and you basically multiply it by the collision rate. This is the collision, probability with all the matrix elements and delta function included. These are the occupation factors that come from Fermi statistics. So you basically sum over all initial and final states. You divide it by 4 to make sure that you do not double count, and you get basically a new current. Okay, that comes from the shifts. And the other effect of these collisions is that when they happen in the electric field, in the presence of electric field, and your center of mass of the two electrons gets shifted, there is a potential energy change associated with that. Okay, so when you write down the energy conserving delta function, you need to change to take into account this change in the potential energy during the collision in the energy balance. Okay, so that's the other effect of these shifts, and basically this leads to the fact that the usual local equilibrium distribution function does not nullify the collision integral anymore. So the collision integral becomes a generation term. There is a linear and E term hiding in it, and it leads to basically corrections to kinetics. So when you put everything together, right? So maybe like this, the collision integral, the usual collision integral, which acts on the deviation of the distribution function from equilibrium, becomes this relaxing kernel and an additional generation term, essentially, that you must take into account the kinetics of such electrons. Okay, so probably this is, I will not go over details of the procedure, but essentially when you take both of these effects into account, you end up with a conductivity tensor that is essentially anti-symmetric in its indices. So we're really dealing with Hall effects. These shifts contribute to the anomalous Hall effect in the hydrodynamic regime when electrons are not colliding with impurities, but they are colliding with each other. And basically, it turns out that the associated kinetics is tricky. Now working on applying these ideas to specific system and advancing them with Songchi Lee and Sasha Levchenko. Okay, but some preliminary results can be flashed in front of you. So if we take the paradigmatic model in which all these anomalous effects are usually studied, the 2D massive Dirac model. Okay, so this is a Weil Hamiltonian, but in 2D plus some mass term. Okay, so everybody knows what the spectrum looks like, right? So well, one can easily calculate these collision, these shifts for this model. Notice that these shifts basically are zero when all particles are on the Fermi surface, when all energies of the particles are on the Fermi level. Okay, they basically do not know which way to shift. Which pair is stronger, so to speak, the initial one or final one. So this shift vanishes on the Fermi surface. So you actually need to take into account the dependence of distribution function, energy dependence of distribution function. And when you do this, it's very similar to calculating the thermoelectric effect in the Fermi liquid. So overall, basically, the expression for sigma xy ends up being as follows. So it's proportional to the square of the temperature. Okay, and this square of the temperature is divided by the Fermi energy, essentially counted from the bottom of the conduction band, right? Okay, and this factor here is essentially the non-probabilisticity parameter known from semiconductor physics. Okay, it tells you that the effect vanishes for p squared over 2m dispersion, like it should for Galilean invariant systems, essentially. Okay, so you can basically say that this t squared dependence is as generic as it comes. Okay, so any correction to anything in a Fermi liquid will be t squared. Okay, so and you would be right if you said that, but one can show that essentially this overpowers the Sommerfeld type corrections to the usual intrinsic no, not even intrinsic, intrinsic plus side jump plus whatever you want to add to the whole connectivity. So this is basically vanishes with temperature, but it provides the leading temperature dependence of that quantity. Okay, so in that sense, it's sort of important. Okay, so fine. We talked about shifts. We talked about anomalous Hall effect that comes from them. Okay, from these collisions. What else? Okay, what else is interesting here? So far we talked about the shifts again, which I defined as the change in the position of the center of mass of the two colliding electrons before and after the collision. But I can view this essentially as the electrons collisions rather taking electronic number between the fluid layers during the collision. And of course, if they collide and shift, they take any additive integral of motion with them. Okay, so in particular here, there is R and there is 1 in front of it, right? I talked about essentially transport of electrons, which was associated with these shifts. But these collisions will transport momentum across the fluid layers. They will transport energy between the fluid layers. They will transport, in principle, angular momentum, and so on and so forth. Okay, so there's this whole hierarchy of effects that are related to these shifts. And in the remaining, I don't know, 10 minutes, I would like to be not particularly precise, not just because, you know, these are things that I kind of want to think about, but have not thought about in depth yet. But I think they're very interesting. I would like to kind of intrigue you a little bit and show you that there is a big field basically that opens up once you start thinking in this direction. Okay, so here I give you another example of a quantity that can be considered. It's this hybrid shift. You basically consider transport of momentum due to shift during the collisions. And basically, if you play the same game I played with anomalous Hall effect, you realize that this is essentially stress tensor. Okay, so if I take this quantity, I multiply it by the collision rate, I will get the rate of momentum transport. So this is related to the stress tensor, and this will be related to viscosity, for example. Okay, so if I put energy there, I would get some sort of thermal Hall effect and so on and so forth. Okay, so let me show you how this basically pans out. And instead of solving equations, I will show you what happens when there is rotational invariance in the system, and then basically pose this question, like, how would you get this if you didn't have rotational invariance? And basically you get it from these shifts. So let me show you what's going on. Let's think about the general structure of hydrodynamics, how you build it. Okay, so if there are additive conservation laws in your system, they affect the way the local equilibrium distribution look like. Okay, and that's your starting point for building the hydrodynamic equations. So if energy, if number and energy of particles are conserved, we know that the local equilibrium distribution function looks basically like this. There is some Lagrange multiplier essentially for energy, which is 1 over temperature, which is possibly space dependent. There is a Lagrange multiplier for the number of particles, the chemical potential, which is also space dependent. If you add momentum conservation to this list, okay, you get another Lagrange multiplier here, which ends up being the velocity of macroscopic flow of the fluid, this U of R. Okay, so what happens if there is an additional conservation law associated with the angular momentum conservation, and there is an internal angular momentum of the particles? Okay, this can be spin, or this can be, you know, if you think about the particle that is a dumbbell, right, you can think about the center of mass motion, but the dumbbell can also rotate around the center of the dumbbell. So that's your internal angular momentum, the sort of classical version of the internal angular momentum. So what is then the local equilibrium distribution function for this case? Okay, so the answer to this is essentially very well known. Okay, so you add another Lagrange multiplier, which is basically angular velocity of the rotation of the fluid. And if you want to be in local equilibrium, essentially your particles need to rotate in sync with the liquid, and that's why this angular velocity, this Lagrange multiplier, ends up being, you know, half of the curl of this velocity of macroscopic motion of these particles. Okay, so what is notable here, and this is this internal angular momentum of your particle. What is notable here is that this local equilibrium distribution function depends now on gradients of U. Okay, so basically that means that if you tried to obtain it from the usual local collision integral, you would always fail, okay? So you need actually to take into account the non-locality of the collision integral. And of course, in general, collision integral is a non-local operator. So you need to take into account non-locality of the collision operator to get this. And it is these shifts, that allow you, really not just shift, but these hybrid shifts, which involve both coordinate and momentum, that allow you to get the right distribution function, the right local equilibrium distribution function. Okay, so in particular, it is this antisymmetric part of this little pi that I defined, which can be shown to be related to the this internal angular momentum that is related to the appearance of this term. Okay, so that also tells you that if you do not have rotational invariance to write this down, but you want to know the first gradient correction to this local equilibrium distribution function, you must take into account this non-locality of the collision integral. Otherwise, there is no way to do that. Okay, so just to briefly show what this leads to, and what it is important to, let me introduce two effects to you. So the one is chiral vortical effect for, in particular, Weyl fermions, but it can be generalized for anything. Okay, so if you take a single species of Weyl fermions, obviously it lacks inversion symmetry, right? So these fermions have a sense of chirality. The Hamiltonian has a sense of chirality, and the particles itself are helical. Okay, so the expression for the currents in a liquid of such fermions contains the usual piece associated with macroscopic flow, but in principle, by symmetry, there's another term allowed, which is proportional basically to the curl of the macroscopic velocity. Okay, so of course, inversion has to be broken because you have a polar vector on the left-hand side and you have an axial vector on the right-hand side. So inversion must be broken. But if it is, there is such a term in the expression for the current. Okay. So basically, I would like to show you that this non-locality of the equilibrium distribution function will lead to this chiral vortical effect. And this is done very basically in a very simple way, and I am borrowing this discussion from the work by Misha Stefanov. The current, of course, is just two contributions. It's the usual ballistic current and magnetization current, curl of magnetization current. Remember, these while fermions have magnetic moments, so if the magnetic moment is non-uniform, there is an associated current, okay, curl of it. Okay, so you take this local equilibrium distribution function that I derived, and you calculate these two currents, okay, and you get a current that basically flows along the vorticity of the liquid, okay, curl of U. Okay, the expression is very much similar to the expression for the chiral magnetic effect current, with magnetic field being substituted with the vorticity. Okay, they have the same symmetry properties. Okay, so again, if this is for a system that is rotationally invariant, if the system is not rotationally invariant, there is no way basically to obtain this distribution function from thermodynamic considerations. So one really needs to take into account this shift that I talked about to get this effect. Okay, so to consider this effect in crystals, okay, which lack obviously rotational symmetry. Okay, so this is kind of an academic question because, you know, in a crystal there's always the other Weyl point that will cancel this, so you need to bias them, and it already makes it very, very hard problem from a practical point of view. You need to, I don't know, use chiral anomaly or something like that to bias them, the two valleys, and then rotate the crystal, or take this electronic spoon and stir the electronic liquid. So this is an academic question, but nevertheless, it's a very cute question. Okay, so another physical phenomenon that comes from these shifts is the so-called Hall viscosity. Okay, and in particular, this anomalous Hall viscosity that you get without magnetic field, but with some magnetization present in the system. So if you look at previous works, it's typically done for gapped systems, like Hall effect state or fractional quantum Hall effect state. Okay, but you can do it also for metals. Okay, and in principle, how to get this Hall viscosity from a magnetic field from Lorentz force is written in textbooks in physical kinetics in this 10th volume of Landau Lifshitz. But basically, you can also get this Hall viscosity from collision integral, not from some single particle spectrum as typically done in literature, but from collisions where viscosity is supposed to come from. Right. So, sorry. Let me tell you what this Hall viscosity is. So if you look at the Navier-Stokes equation, essentially, Newton's second law for momentum, there is usual, Euler force. There is basically a drag force associated with the friction of the fluid layers, and there is this Hall force, Hall viscosity force, which is basically a lift force, right? So if your fluid layers move like this, there is basically a force perpendicular to this direction, okay, which is described by this Hall viscosity. And there are experiments now that can measure that, in particular from Andrea Games' group in Manchester. So this is a measurable quantity apparently, and one can think, how to get it, not from magnetic field. The way they got it was from magnetic field, but from magnetization, essentially, from band geometry, from quantum mechanics. And it's very easy to see that this local equilibrium distribution function that I got for the isotropic case leads actually to a contribution to this Hall viscosity. You just go through usual procedure based on kinetic equation, multiply kinetic equation by momentum, integrate over all momenta. Okay, and essentially you get this Hall viscosity term, and the expression that you get for this term is surprisingly similar to the expression that this Israeli folks and Nick Reed got based on essentially adiabatic transport for gapped systems. Okay, so this is for a compressible system for Fermi fluid. Okay, but the expression you get is exactly the same. So if you don't have rotational symmetry, basically these shifts that I talked about are a way to obtain this anomalous Hall viscosity terms from Boltzmann equation from the collision integral. Okay, so this is something that needs to be done. I hope we will do it with Sasha and Sang-Chi. But this is just a hint that this is an interesting subject at this point. Okay, so at this point I arrive to my conclusions. Okay. Okay, and the main conclusion is that band geometry does manifest itself in two-particle collisions. Okay, so the collision integral is sensitive in a non-trivial way to the Bloch wave functions of the electrons. Okay, so these collisional coordinate shifts are responsible for some, effects in hydrodynamics that are unique to electronic liquid rather than, water and Navier-Stokes equation, right? So, of course, water is better to study Navier-Stokes equation than electrons. Okay, so these shifts, these ideas based on shifts lead to anomalous Hall effect, chiral vortical effect, anomalous Hall viscosity. I didn't talk about it, but also there is a thermal Hall effect and so on. So it seems like this chiral hydrodynamics in solids is actually a subject, is a rich subject, which I hope will be developed in the immediate future. And who knows, maybe graphene on this hexagonal boron nitride with this gapped spectrum is the simplest system that can allow to study all these topological currents in the hydrodynamic regime. So with that, I am done. Thank you very much for your attention.
Yeah, thanks, Dima, for a very nice talk. I suppose there are questions. So if you have questions, please speak up.
Maybe I can ask about something you just mentioned at the end. I'm sorry, I missed the earlier part. So you mentioned a connection between the Hall viscosity and the shift So exactly what system are you referring to and how general is that?
So I was not really referring to a particular system. My point was that it was like this. So the usual viscosity comes from momentum transfer between the fluid layers during just momentum transfer between the fluid of layers. Okay, and that comes from collisions essentially.
Mhm.
So these shifts that I described, they take all the additive integrals of motion with them. So they transfer electron number between the layers, and that was the origin of the this anomalous hydrodynamic anomalous Hall effect. Okay, but they also take momentum with them, and that is that looks like it leads to this anomalous Hall viscosity essentially in the Navier-Stokes equation. They also take energy with them, so there should be a thermal Hall contribution, thermal Hall effect contribution because of them. So it really this transport of the additive integrals of motion between the fluid layers that is responsible for the appearance of all these quantities. In this sense, it's completely generic. It's not for any system. It's just what happens when you have non-trivial momentum-dependent block wave functions in your Brillouin zone.
Okay, thanks.
Mhm.
So are there further questions? Sorry, world is in turmoil here. Are there further questions?
There is one question you didn't ask me, actually, because what I've been telling you is a little bit counterintuitive, right? So if two of us, or myself and any of you, will run into each other, our center of mass will not be shifting. Okay, so this is kind of weird that I'm talking to that there is this crystal electrons are colliding and shifting all of a sudden. That has the feeling of this, remember this old German guy pulling himself out of a swamp, pulling on his hair or something like that, on his ponytail. But the thing is that the resolution of this is that this is actually a three-particle collision in the crystal. So it is the crystal, this infinitely massive crystal behind it, that sort of can absorb, which is a source and sink of a center of mass displacement. So in relativistic physics, where there is no crystal, obviously, it is the fact that center of mass or center of energy is poorly defined when particles are spinning. So what is the angular momentum depends on how you define the center of mass and vice versa. So in the case of a crystal in the non-relativistic physics, it is really the three-body collision that is behind this shift. So it's just the crystal basically absorbs any momentum, any center of mass displacement of the electrons. Okay, so that's the resolution. But this is the question I thought I would be asked, but I figured I will still answer it. But maybe there are other questions too.
May I
Sure.
ask a quick question? So there I am. So regarding Hall viscosity in fractional quantum Hall liquids, since you just briefly mentioned it, I mean, there you have a combination of a just magnetic field response and the topological part. I mean, the Hall viscosity really encodes the Venn-C shift as well. So you should be able to read off the topological numbers there. I'm just wondering, is there, and this formalism kind of distinguish, can it work in that strong field regime where things are gapped and you have Landau levels, and B, can it distinguish between the topological parts and just vanilla magnetic field part of the Hall viscosity?
The short answer is I don't really know, but I suspect that no. Basically, you see that in a sense, the hydrodynamics is very much restricted by symmetries. So of course, the only thing that we can hope for is to provide mechanisms for coefficients that are allowed by symmetry. So the observation that I made is that for this rotationally variant system, you get an expression for Hall viscosity that is very much essentially the same as you get for a gap system. Okay, but you know, a coefficient is a coefficient. That's it. But
Yeah.
I don't think you can extract something super deep out of this number essentially.
Okay. Well, thank you.
But I don't really know. Wait.
Yeah.
Are there more questions? I mean, I have a very technical one, I guess. So I was thinking if you were to derive this, say, from a like higher level Keldysh thing, and you do the gradient expansion, like the effect you're describing, is this something which comes up doing the gradient expansion on the collision integral? Is it one order higher than what one usually does, or?
So the effects I was talking about are essentially effects of interband coherence. So what happens is that, how to say this? Basically, yes. So especially for the non-locality of the collision integral, right? So essentially, the local one is obtained at zero order in this gradient expansion, and the non-local one, the part should be essentially the first correction. The condition, the correction to the current, however, is a little bit different. It essentially comes from interband coherence induced by collisions. Just like with anomalous velocity, when you drag an electron, you know, it cannot adjust adiabatically to the instantaneous wave function. So there is a mixture of different bands, and that leads to anomalous velocity. When you collide them, you also essentially introduce interband coherences, which then change the expectation value for the current. So it's sort of a mess. I think basically I haven't gone through this procedure because I think it's absolutely horrible to do it. And given that these simple physical considerations lead to reasonable results, I kind of willing to stop there because I think to derive it from Keldysh is pretty insane. Okay. But these are the two mechanisms, you know, first one, the correction to the collision integral, the gradient correction to collision integral, and introduction of interband coherences during the collision. I am pretty sure they are responsible for these effects that I was talking about essentially. So if you remember, I talked about correction to the collision integral linear in the electric field. Okay. So basically that correction, linear correction in the electric field, should be there if the band structure is curved, essentially. That's the point.
Thank you. Are there any further questions? Doesn't seem to be the case, so let's thank Dima again. Thank you very much.
Right, thank you for your attention, guys.
Well, let me stop the recording.